Now, I want you to recall that when we're at a high flow rate, the nature of the flow in the pipe changes. And so in our case, whenever our Reynolds number increases beyond 4,300, it becomes turbulent. So turbulent flow is filled with a bunch of transitional eddies that are variable size and duration. They're going to come and go. They're going to change. And that gives us a slight problem because if we stick a velocity sensor inside a turbulent flow, this is what we'll end up getting. So this is just the velocity at any single point within the flow. And as you can see, there's a lot of variability. There is a lot of fluctuations in the flow at this point. And this gives us sort of a problem because in laminar flow, we are able to exploit our knowledge of the nature of viscosity and how the flow is ordered and how it's going to flow. We can't really do that with turbulent flow because we have these chaotic speed measurements. Fortunately for us, we do not care about these fluctuations in the flow. We just want to be able to calculate out the pressure difference and the volumetric flow rates, which we can do. So if I look at this picture here, so this upper picture up here, what we're looking at is what our laminar flow looks like. It's a parabolic curve, and so we're able to sit there and go, okay, well, half the maximum velocity, we have the average velocity, and we're able to calculate things out. The thing is, when we look at the second one, this guy right down here, what we're looking at is a turbulent flow. Now, the turbulent flow, if you look at it, ends up developing much differently than the laminar flow. As it enters the pipe in the entrance region, the friction effects are felt through the fluid much, much quicker, which is why you can see there's just this very little bit of increase on the wall before we end up hitting that inviscid core. And that inviscid core, unlike for laminar flow, doesn't stay around very long because the effect of all these turbulent eddies really mixes the momentum across the pipe diameter just like it would mix the dye. As the concentration of these turbulent forces become more uniform, so does the velocity profile. And as you look at it, the velocity gradient of the wall is much steeper than laminar flow. And so in that small area, you have much higher stresses, but you have more of the center part, which is basically inviscid. And so it's really going to play around with how much friction's felt through the entire pipe. So how do we go about taking a look at this? Well, in 1800, Coulomb was looking into this phenomenon, and so he performed a lot of experiments, and he showed that the surface roughness had an effect on the pipe. And so remember we talked about previously that the surface roughness, if this is my nominal inside diameter of the pipe, well, the pipe isn't completely flat. So actually if I zoom this in, so what I'll have is I'll have a rough surface here on the inside. This is what it should be. Well, the average or the nominal deviation from that idealized center we call epsilon. And where epsilon is going to be what we term as the surface roughness. So after Coulomb did this work, what he calculated out is we have this concept of the surface roughness ratio, which is going to be epsilon over d. Now, this table is from the textbook, and it shows the epsilon values for a bunch of different materials at different states. And you'll also notice we've got them in feet and millimeters. So we have to be very special attention to what unit system that we are using to be able to calculate out which epsilon over d roughness ratio comes into play. So why is this important? Because if you remember when we talked about the Darcy friction factor is a function of three things: Reynolds number based on diameter, epsilon over d, and shape. We'll talk about shape later. So Coulomb came up with this idea that the roughness ratio affects the pipe's grade. So in 1939, Colebrook came up with an expression to calculate the friction factor across all smooth and rough conditions. So before, when we have laminar flow, we can sit there and go, okay, it's 64 over the Reynolds number. So the Colebrook equation states that 1 over the square root of F is going to be equal to negative 2 log base 10, the surface roughness divided by 3.7 times the diameter, plus 2.51 divided by Reynolds number times the square root of F. And so this is the Colebrook equation. And actually, there's only one O in Colebrook. And the Colebrook equation is how we can calculate out friction factors, Darcy friction factors, across any scale, whether it be laminar or turbulent. Now, of course, we look at this, and aside from the fact that it's a log-based unit, it's a log-based equation, we also have the square root of Darcy friction factor on both sides. So this one becomes a lot of guess and check kind of things when you're trying to calculate out the Reynolds number. So that was in 1939. And so in 1944, so let's just 39, oops, not 13, 1939. So in 1944, 5 years later, a scientist went, wow, that's a real pain in the butt to try to calculate every time. And so what he did is he plotted the Colebrook equation manually. And he did it across a bunch of different surface roughness ratios and different Reynolds numbers. And he developed what was named after him, the Moody chart. And so that way you can use the Moody chart. Now, why it's not as exact as using the Colebrook equation, because we're going to read off a chart, what it did do is made things a lot quicker to calculate out. Especially when you're looking at 1944, when you're still using manual computers and slide rules. Colebrook equation still took a little bit of time to calculate out, where the Moody chart, you can do it really quickly. Now, true, with things like Excel now, I can sit here and calculate out a friction factor very quickly because I have an Excel sheet set up for it. In fact, when I write problems, I use the Excel sheet to calculate out what the friction factor should exactly be based off the Colebrook equation. Of course, when I'm grading things, we're looking at a chart, so we give you a little bit of leeway of, oh, yeah, you're kind of close to it. But anyway, so let's take a look at the Moody chart.